everyone, and thanks for joining our webinar on conventional reservoir solutions, optimizing your primary and secondary oil recovery process. My name is Adrian Thomas. I'll be your moderator for today. I'm a product manager here at CMG, covering our pre and post-processing products, builder and results, along with something you'll see today, our CMG Petrel plugin. So our agenda today will cover a few topics. The first will be our products and solutions in the conventional space. Then we'll move into a real-life example of a brownfield water flood optimization study. At the end, we'll leave room for some Q&A. So before we begin, we'll start with a few housekeeping items. The first, we'll be recording this session today, and we'll be sending it out along with the presentation for you to review at a later date. Depending on your internet connection, you may experience a bit of lag in the presentation. We recommend plugging into an Ethernet cable if possible. We've also muted your mic, but if you have any issues, feel free to use the chat window where a moderator or someone will be able to assist you. Also, you can use that same chat, or possibly there's a question section where you can type any questions you have throughout the presentation. Again, those will be addressed at the end of the webinar. So with that, I'm very excited to introduce our two presenters, Jeremy and Amin. I'll pass it over to them to give a brief intro of themselves. Thank you.
Great. Thank you very much, Adrian. I am Amin Dehani. I'm a senior reservoir simulation engineer with CMG. I've been with CMG for almost 4 years now and been in the industry for over 10 years, doing production engineering, production operations, and reservoir engineering. And over the past 4 years, been more focused on the reservoir simulation aspects, and also integrated production system modeling with CMG. I'm very excited to be here today and to present the results of our brownfield water flood design and optimization that we did through our solutions and applications. So with that, I'll pass it to Jeremy to present you the first part. Thank you very much.
Great, thank you, Amin and Adrian. Really appreciate the intros there. So I'll be the one starting you guys off today. My name is Jeremy Walter. I'm a product manager here at CMG. I've been here going on 15 years. I actually started as a reservoir engineer, working on projects all over the world on thermal, conventional, CO2 EOR, CCUS, geomechanics. I then moved into a account management side of the business for a while, and now I'm the product manager that looks after some of our core solutions, including the conventional solution that we will be showing you today. Sorry, I think there's just a little bit of a delay there. There we go. So in terms of what CMG is focused on now and going into the future, we really have 4 primary areas in order to build out what we consider our long-term value to our clients. And so this consists of our core offerings, which are the historic offerings that we have brought to the industry, providing solutions in the oil and gas space for everything from conventional to EOR and complex processes. As well, energy transition. We have a lot of investment into here over the last couple of decades, and our tools are being used around the world, particularly for CCUS, hydrogen, geothermal, etc. On the production modeling side, we also have solutions for modeling of integrated production systems, as well as facilities and production tools, and then strategic partnerships with various key contacts and other organizations around the world to provide best-in-class offerings to various disciplines and various solution sets. So what I'm going to be talking to you about today is the conventional solution. So I'm going to start by actually going through what our conventional solution is, and in terms of the reference point of the software and the tools that are behind it, that drive it. Then Amin is going to go through and actually demonstrate the application of that on a real world problem and show you how all of the different pieces come together to give a unified solution and approach. Now, why do we need to worry about this at all? Well, all of our subsurface operations are complex, right? And if you know me at all, you've heard me say it before, we have one of the most uncertain engineering challenges in the world because we cannot see what we're doing, right? It's synonymous to me asking you right now in this video call, what type of shoes am I wearing, right? You don't know. I could be wearing sandals, I could be wearing slippers, I could be wearing dress shoes. You don't know, right? It's not until I give you some sort of point information that you start to get an idea or a picture of that. So if I say I'm wearing closed-toed shoes, well, that narrows that gap down. And if I tell you the color, it narrows it down further, right? And so as we try to obtain information from the subsurface, we're trying to build out that picture, that image of what's there. But at the same time, there's still going to be uncertainty and unknowns. So it's a matter of how do we fill that in making an operational decision. And so the overall, I'll call this the generalized subsurface workflow, where what we're essentially doing is collecting the sort of data from the field. We then use that to generate a realization, a geological realization or geological model, where we're incorporating all the information that we have. And we might have numerous sets of these realizations or these models. This then gets put into a dynamic model setup where we are actually looking at running it out with time, making operational changes, seeing what the impacts are. We'll run different scenarios of this in order to then be able to interpret the results, the risk, and make decisions. At the end of the day, we want to look at how we can optimize our operations, improve the recovery and the value of our assets, as well as assess and mitigate any sort of risk that could be inherent in the field. And so what we're looking for is a set of tools or a specific solution, which when applied together provides us these types of solutions to the objectives that we have as stakeholders. So the CMG general software offering has a number of different pieces to it. We have our pre and post-processing tools, which allow you to visualize the inputs and the outputs. That's Builder and Results. We have our 3 simulation engines, and these are this historic backbone, the historic engines that drive the solutions coming from CMG. IMEX is our black oil simulator. GEM is the compositional simulator used quite widely for unconventionals and energy transition. And STARS is the thermal simulator that companies around the world have been utilizing for a very long time for steam, chemical, and advanced processes. These are all working together with our CMOS uncertainty tool, and everything can be coupled into our cold flow integrated production systems modeling tool in order to model the facilities and the entire system of the subsurface and surface operations. And everything is wrapped within the ability to deploy in cloud. Now, for the conventional solution specifically, what we're actually doing today is packaging the very particular parts of this to create a solution which is focused at one particular task. So in conventional space, you're talking primary, secondary, we're not talking EOR. And so we want to simplify and make a fit for purpose workflow. Something easy, simple, fast. So it doesn't matter if you have a lot of knowledge and simulation in the past. With this particular solution set, you'll be able to start at wherever you might be, whether it's just basic information from the field or actual geological models, build up quickly and rapidly to a simulation model, optimize that, and have a path forward for your asset. So what are the different pieces of this? The first one is Builder, our pre-processing tool, the ability to build out the model very, very quickly. So this is a menu-driven, wizard-driven tool where you can display, edit, QC your data. You can create data sets by importing your log or LAS information. If you have maps, instead of a geological model, you can bring the maps in and use those to build it. We can import from Rescue, RescueML. We can import from a variety of geological modeling packages that are available on the market. As well, we also have created a Petrel plugin. And I'll discuss that in a little bit because that is also a key piece to the conventional workflow and solution. It's being able to pull things directly from Petrel over into Builder for use. Along with this, we also have process wizards that were created for rapid setup. So you can have pattern well creations, vertical lift tables created very quickly. Next is the simulator, the engine, in this case, IMEX. This is our black oil simulator. It's the fastest black oil simulator in the world. Every benchmark that we've done where we go head to head, it always comes out on top. It enables us in the rapid planning of our operational decisions, right? We want to reduce the time frame and accelerate the speed to a decision. So that incorporates both the reduction in the setup time as well as the reduction in the runtime. It's a seamless integration with all the other CMG tools. It's compatible with other industry standard geomodeling and production packages. It's cost effective and it's available in a variety of environments. In terms of the technical functionality, you can model everything from heterogeneous data sets and geomodels to naturally fractured reservoirs and even discrete fracture networks. And it can be applied for primary, secondary, as well as gas storage scenarios. In terms of some instruments within IMEX, which can help facilitate the analysis of these types of conventional fields, we have the ability of defining aquifers. So if you have an aquifer attached to your reservoir, you can see how the impact of that could impact your production. Flux boundaries allow you to run the larger model, then actually take out a subsection of that, and the fluxes, the fluid movement in and out and pressure changes are actually still accounted for. And so in this way, you can actually model a smaller area of the model much quicker and do numerous scenarios before then applying it back to the large model while still having the overall complexity of the simulation, the situation applied. And then tracers, the ability to actually inject or deploy tracers within your model, either in the simulation just to get an understanding or to mimic what you might be doing in the field in order to see where the fluids that you're injecting or where different components might be actually going. As I mentioned, it is the fastest black oil simulator on the market, and we continue to push the boundary on that. In the last couple of releases alone, we've actually seen a 2 times reduction in runtime or increase in speed. And so this is something that we just continually strive for. Speed and stability are 2 of our primary tenets in all of our products going forward. After you've done running, then you come to results. And here, what I'm doing is looking at, from a qualitative sense, the understanding of the reservoir itself, of the fluid movement. So I can use streamlines, isosurfaces, histograms, all sorts of tools at my disposal to gain that understanding. As well, if you need the quantitative methodology, you can look at flow allocation metrics. You can actually track items with distance, cross plots, and the normal time series plotting that you would expect. We also have the ability of doing auto repeating of plots. And so after you create a plot for a well, if there's other wells that can have a similar plot, it will automatically create those, really reducing the time to making decisions. This brings me into the CMG Petrel plugin, which has been created and deployed through the Ocean framework. And so in order to help facilitate everything I just showed you and the movement from a geological modeling into the simulation side, this plugin allows us to very quickly and easily move data between the 2 products. And so with this, you can export the model grid and static properties directly into CMG. You also have the ability of importing back. So after you run your simulation model, you can actually export it from the CMG results back into Petrel to be able to look at in reference to the overall grid and system that you're evaluating or investigating. And then lastly, we even have the ability of simulating directly from Petrel. So in this case, after you build up a dynamic model in Petrel, you can actually use the same plugin to launch and run an IMEX model directly. And so you don't even need to necessarily go into Builder in order to complete your dynamic model case. This is also great if you already have any sort of simulation model created previously in Petrel. You can just use CMG and use IMEX as the engine on the back end in order to run that. And shown here in this GIF, you can see that quick running of it. After it ran, we could bring the results directly back and watch them, their results. Lastly is CMOST, and CMOST is the tool that we utilize in covering off our uncertainty space and in optimizing the overall problem. And so, as I mentioned at the beginning, there's just loads of uncertainty that we deal with in the subsurface space. So how do we answer these what if questions? How do we understand the unknown parameters and the unknown values that could be impacting our operations? This is what allows us to automate the process and quickly find history matching. We can use machine learning to fill in the gaps, forecast probabilistically, not deterministically. We're actually looking at P10, 50, 90 outcomes, in order to then verify and understand the geological data that we have and make those decisions. Now, CMOST has the leverage of different optimizers in the back end. And with these, we're able to quickly move from a design and learning phase where we are filling out that uncertainty space to then utilizing machine learning and utilizing these proxies in order to drive down to a solution very, very quickly. And just like you see here in this image, that's exactly what we're doing in trying to find a history match. And lastly, it also has the what I consider to be one of the most powerful tools in a reservoir engineer's tool set, which is robust optimization, where now I'm taking into consideration all of the unknowns, which could be affecting my potential outcome in the field, and I'm creating an optimization scenario based on all of those. And with this, what I'm able to do is capture what the one path forward should be in the field that gives me a beneficial outcome, whether it's net present value or recovery or whatever it might be, based on those unknowns. So even if I'm off with my porosity or permeability or geobody arrangements, I can still get a valid path forward that provides the company and the stakeholders true value in the long term. So with that, I'm now going to pass it over to Amin, who's going to be showing you and demonstrating the application of this very easy to use packaged workflow on a real world condition. Thank you.
Thank you very much. Thanks, Jeremy, for the great presentation of the solutions and the tools that we have at CMG. So for the next part, what I'm going to be presenting to you is a case study that we did, and you will be seeing how these tools and different solutions actually come together to actually be utilized in a seamless workflow to achieve a goal. So for our case study, what we were doing was a water flooding for a brownfield, and the intention was to optimize this water flooding. So how do we judge the optimization? So what is our goal? How do we call a solution an optimum solution in this case? So we should be looking at two aspects. One was to maximize the oil recovery. So that's what we are looking after. We want to get the maximum oil out of the asset. But at the same time, we have to look after our investment too. So how much we're going to spend money, what is the balance point? So at the same time, we have to look at the net present value of the investment, the NPV. So if we make sure that we maximize the oil production, the oil recovery, and at the same time, we've been able to maximize the NPV as well, then with this, we will be able to kind of de-risk the project. So we will de-risk the investment while making sure that from technical aspect, we are following the guidelines. So let's look at the case study. Let's look at the project that we did. So what you see here on the top right is the 3D view of the reservoir under study. And it was a faulted reservoir with 22 years of primary production, and through reservoir engineering studies and assessments, it was decided to implement water flooding for the next 15 years to maximize the oil recovery. Why? Because as you see in the bottom left plot, this shows the oil rate of the field a long time. and this field was experiencing a decline in oil production. And as you can see here, maybe if I point it with the pointer, as you can see here, the field was starting to decline in terms of oil production. So the intention was to implement a water flooding using 2 injector wells to increase the oil rate. But here, that's the goal. But we have to remember, any reservoir study is a multidisciplinary study. So meaning that reservoir engineers who work on the dynamic model, they need to be constantly communicating with the geomodelers. So the static model needs to be, we need to be able to seamlessly and effectively update the dynamic model. So that is why at CMG we have developed a tool called CMG Petrel plugin, so that, as Jeremy explained, you can easily transfer the geomodel from Petrel to CMG's pre-processing tool, which is Builder. I'll show you this in action after the presentation. So now let's look at let's kind of remind ourselves about the main aspects of any dynamic model. So we have a container down the ground, what we call a reservoir. What are the container is the rock, and what is inside that we want is the fluid, the oil. And then we need a tool to extract and recover this. So it is really important for any effective dynamic modeling for the engineers, for the reservoir engineers, to be able to input the rock properties such as porosity, permeabilities, be able to change them easily to make sure that the reservoir is characterized properly. And then again, the ultimate goal is the fluid. So we have to have the same tool. We have to be able to define the fluid, all physical properties of the fluid, viscosity, oil formation, volume factor, the solution gas, everything. And then we have to remember the rock and the fluid are sitting together. So the interaction between the two is really important. How do we define this interaction? How do we quantify this? Is through relative permeability curves, capillary pressures. So having different models at your fingertip, being able to import tables if you have lab data, it is really important too. And in the next step, if you don't initialize the model properly, if you don't have different options, different tools to make sure that the reservoir is initialized properly and it actually reflects the real situation, you won't be able to get the results, the correct result, whether it's in the history matching period or forecasting. If you don't get the first step right, you won't be able to physically and realistically match the behavior of the reservoir. And as I mentioned, we have the container, we have the fluid. Now, what is our tool to get the oil out of the reservoir? It is wells. We do this through drilling and completing of production wells, or if you're looking into any enhanced recovery, we can do this through injection well, whether it's water flooding, gas injection. So having different tools to be able to quickly define wells, operate the wells under different conditions. For instance, imagine that you're in the history matching period. You're trying to first find out a model that actually represents the behavior of this reservoir, this uncertain reservoir. So you have to be able to easily and quickly import the historical rates, pressures, everything. And also, in real cases, you can easily, run into hundreds of wells. So managing these wells and QCing the input can be quite overwhelming. So we have different tools at CMG to help you QC the input of the wells. For instance, we have a tool called Well Event Timeline View. What this tool does for you is it visualizes when each well is coming online, if it's getting shut in, and it will help you QC the data, making sure that the wells are operating the way they're expected to. So this was an overview of like the inputs, that we typically do in terms of dynamic modeling. So for this very case study, let's have a pick at the results and like what we were looking after, and then let's jump into a live demo to actually see this in action. So as I mentioned, the goal for this study was to maximize the field oil recovery. And through studies, it was decided that this will be done through water injection. But is the water injection the answer? Can we just drill 2 wells and start injecting water and expect to get the best and the optimum result that we want? We might get a better results. That's okay. That's an answer. But is this the best answer? Is this the optimum answer? And in any real case, we have some limitations. We are constrained by some factors. For instance, for this study, we had access to a limited amount of water for injection. We didn't have unlimited amount of water to assign to the injectors. So even if we had, is the answer like just injecting as much water as we want? Is this the answer? Probably not. So in this case, the problem was even more complex. We have a limited amount of water and we have 2 injector wells. So where do we drill these injector wells? And then how do we divide this water between the 2 wells? What should be the apportionment between the 2 wells? Where do we complete these injector wells? And then when do we actually start the injection? Should we start right away to inject water, or maybe the answer is wait a little bit? And then how do we judge if the solution is optimal? Again, by 2 aspects. We have to look at the cumulative oil production. That's the technical intent. That's the technical goal. We want to produce more oil. But at the same time, we want to look after our investment too. So that is why we have to maximize the NPV at the same time. So in this plot that you see on the top right, along the horizontal axis, I have different simulation models that I ran. And then on the vertical axis, it shows the net present value. And you can see that how our optimizer tool, CMOS in this case, was able to first explore the solution space and quickly find the optimum solution, and over a few simulation model was able to maximize the NPV. So what this plot shows is the cumulative oil production of this case a long time. So the black line is the base case. We just added 2 injector wells and started injecting water 50% of the water available for each well. And then CMOS started to experiment with different injection locations to and automatically create multiple models, as you can see with these blue curves, to find the optimum answer. And the red curve here shows that our optimizer tool was able to increase and maximize oil recovery, which is the cumulative oil production in this case. And as well, I mentioned that the other constraint and limitation that we had was how to divide. So we had only 2,000 cubic meter of water per day available for us to inject, and we had to optimize our water injection scenario based on this much water that we had available to us. So, and ultimately, using our tools, we were able to easily transfer the model from the geomodeling package to our pre-processing, inputting the data, running the simulation, analyzing the results, and also optimize it. So before jumping into the results, the final, cumulative production that we were able to achieve, let's see this in action. Okay, so for now, I'm gonna go to the live demo. Okay, let's start from the first step, which is the geomodeling tool. All right, what you see here is the reservoir under study in the geomodeling package. And as Jeremy mentioned, we have developed a tool called CMG's Petrel plugin. And then with this tool, we're able to easily transfer the data to CMG's pre-processing tool. So how you can do this is using exporting the model and then just pick a name for it. And then after that, CMG's Petrel plugin shows up. And you have two main tabs, the properties and wells. What you see here under properties is the different properties available in the rescue file, and you can pick and choose which property you want to export. And as well, if you have wells with trajectories already defined in the rescue, you can pick which wells you want to export. And then you have two ways to go, either just export the model, or here we have an option here to export the model and immediately open it in CMG's builder. And this is the option that I'm going to choose here. So what it does is that it exports the model and opens the model immediately in CMG's pre-processing tool, which is builder. So as you see, like in a few seconds, I was able to easily transfer the geomodel from the geomodeling package to CMG's pre-processing tool. And then now let's go over the builder options and get a summary of the options that we provide for the users with builder. So for the sake of time, I'm gonna move to a pre-made model. This is the same model that we just exported from Petrel to builder. So CMG's pre-processing tool, builder, is a menu-driven tool, and it has a top-down design, a guided design to help you input the data and create the model easily step by step. As you can see under this model tree view, it has the reservoir components, which is the fluid properties section, the rock fluid section, initialization, numerical, geomechanics, and wells. So let's go over the steps and get a summary of what each step is. So under the reservoir, typically we can change, make modifications for rock properties such as like porosity, permeability, and all reservoir properties and properties associated to grid blocks. And then we have the component section, which under this section, you can either import the lab data. If you have any lab data available to you, you can directly import those lab data. And even if you don't, still no problem. Builder has a lot of built-in industry standard fluid properties correlation. So with minimum amount of data, such as just bubble point and fluid densities, builder can generate the fluid properties for you. For instance, what you see here is the solution gas and the oil formation factor for this reservoir. Or in the other plot, I'm showing you the expansion factor for the gas and viscosity models. So the next step, if you recall, we have the rock properties, we have the fluids, we have to be able to quantify the interaction between the rock and the fluid. So that is why the next section in builder is rock fluid, in which you can enter the relative permeability curves. Again, the same thing as PVT, the fluid properties. If you have lab data, you can easily import them for oil, water, and gas relative permeabilities. Or if you don't have any data, builder provides built-in models so that you can just enter the endpoints, for instance, the coneate water, the endpoints for relative permeability curves, and builder will generate the relative permeability curves for you. And not only that, it also provides you with tools to modify this curve to match the behavior of the reservoir under study. And also it provides three-phase models, everything at your fingertip to change and experiment with different models to make sure that the behavior of the reservoir is captured. And in the next step, we have the initial conditions. As I mentioned, you have to define the reservoir properly. You have to get the first step right. And then we have the numerical section. Remember, we are facing with a very complex problem at hand, so there's no way that we can solve it analytically. We have to use numerical methods, so we need to have some control over it. And then I'm going to skip over geomechanics and tracer for this demo, and the last step we have wells, in which you can define multiple wells easily and define how you want to operate them, their trajectory, depth, and all properties related to wells and how you want to operate them. Once the model is complete and you have all these green check marks here, you can easily run the model through this button here through IMEX, and the IMEX engine will be called and the model will be passed to the engine. It will run the simulation very fast for you, and then you can have the results. So after pre-processing, we have the engine, but the simulation is no good if we cannot have the results in a way that humans understand. So then we have CMG's post-processing tool, which we call CMG Results. That's our tool to help you analyze and interpret the results. So let's look at the results. So this is CMG's results application, a very powerful tool to help you, understand the behavior of the reservoir and to make your decisions, to understand how the reservoir is behaving, and take and make the decisions accordingly. In CMG Results, you can have 3D plots, you can have 2D plots, time series, you can define your own formulas to even define your own properties, and all kinds of tools for visualization and plotting of the results. Let's look at a few plots here. Definitely Results comes with a whole lot more options. I'm just going to walk you through a few options that we have. For instance, this plot here shows the cumulative oil production of the reservoir in the base case without any water injection. So as you can see, after year, say 2025, around this time, we don't have very much of increase in cumulative oil. We had most of the increase in cumulative oil over the first, say 20 years. And then because the field is in decline, then the cumulative oil is not increasing very much. So now let's look at another plot. This plot is after adding 2 injectors to the field. And as you can see, just by adding 2 injector wells, we were able to increase the produced oil from the reservoir. But is this the answer? Is just adding the injector wells is the answer? Is this all we can achieve? Should we stop here? Probably not. And that is why we did the next step that I'm about to show you. But before moving to the next step, the optimization, let's look at a few options and exciting options in results. Another option that we have, like all time series plots, I already showed you. This plot shows the oil rate of the reservoir. Again, you see from 2024, 2025, we are in decline, and the goal of the study is to increase this oil production. And this plot shows after starting the injecting water, we were able to increase the oil production. But again, we want to go further. We don't want to stop here. A lot of other tools, for instance, this tool here, this shows you a streamline of the reservoir, and these streamlines can help you understand the fluid movement. For instance, what I'm showing here is this is our injector 1, and this different colors show how much of the water injected by this well is going to which producer well, and what is the path that the water is taking to reach to each producer well. So if you're analyzing the water injection and let's say you move the injector well further down and you see that water takes a long path to reach the producer wells, and actually sweep and push the oil toward the producer well, this might give you a hint that I might need to change the location of the injector well. So these streamlines are very helpful to understand the behavior. Another great feature that we have is result dashboards. So with dashboards, you can mix and create your own kind of reporting dashboard. So what I have created here is I have the top view of the reservoir. That one on the top left shows the pressure field of the reservoir, the other one is the water saturation, and at the same time I have the side view. And as you can see, I can kind of run the case a long time and visually see how the pressure field is changing. And not only the pressure field, another property such as the water saturation. And you'll see that now that in year 2025, when the injector comes online, how the water is moving and how what is the water saturation close to the injector well, and how the pressure field of the reservoir is changing. All right, so with this, let's move to the optimization stage. So as I mentioned, the answer is not just to inject water. We know that we can optimize it and we can make the best out of our investment. We are spending money to drill these wells and to kind of create the facilities and deploy the equipment to inject water. So the next step is to use our optimizer tool, which is CMOS. This is the interface of our optimizer tool, CMOS. So let's quickly look at the main parts of CMOS and see what tools CMOS provides. So for CMOS is trying to optimize a problem. So for the problem at hand, so we have to be able to define the inputs, then tell CMOS what is the model, then ask CMOS what is it that we are looking after as the output, and we want you to optimize it for us. That is why in CMOS we have three main sections: input, control center, and results and analysis. In input, we define what it is that we want you to modify as the parameter. For instance, here you see this number 8. This means that I have defined 8 parameters for CMOS to change. And also we have different kinds of objective functions, so that we can define for CMOS how to judge the results, when to call a solution an optimum solution. For instance, in this case, we defined the net present value as our goal, as our objective. And you can have very complex objective functions. You can even combine different objective functions, look at the technical side and the monetary side at the same time. Even if you have your own in-house formula, you can still connect CMOS to third-party softwares such as Microsoft Excel, and you define your own objective function there, and CMOS can easily communicate with your own function. And then you define your how you want to run the model, and then CMOS, that's the interesting part, CMOS will automatically generate multiple cases, and then after that runs the cases for you, and then according to the results of those automatically generated cases, it will optimize the solution and decides what combination of inputs will give us the answer that we want. And as you can see, CMOS automatically generated multiple cases for us, and I started to run multiple cases and maximized the NPV value that we are looking for. And as you can see, CMOS was able to increase the NPV by multiple degrees from the base case to the optimum solution. And as well, again, the same story as the simulation itself. If you can't analyze and interpret the results, the study itself is no good. So that is why CMOS comes with its own post-processing tool, its own visualization tool, and it gives you a lot of post-processing tools. For instance, if you remember, one of the parameters that we were looking for was the division of water between the two injector wells. And initially, we just gave it 1-to-1, meaning that 50% of water goes to injector one, 50% to the other one. Let's see how CMOS found the answer. You see that here, CMOS started to explore a wide range, like from assigning 1/10 of the water to injector well, or 10 times more to injector well, and eventually found the answer that like a ratio of around 3.5-to-1 gives the best answer, and it was able to maximize the results. So with this, we can go back and see how much actually this optimum case helped us to produce more. So let's go back to results. All right, so this shows the final optimum solution that our optimizer tool CMOS found for us. As you can see, CMOS moved the injector well here, and injector 2 here, and injector 1 here, and also found the answer for apportionment for us, that around like 1500 cubic meter per day should be assigned to injector 1 and the rest to injector well. Let's look at the total oil production from the field. So what you see here, the red or orange line is our base case without any injection, and then this blue curve shows that our base case for water injection, just adding 2 injector wells, just by adding injector wells, and this was easily done through Builder. We were able to produce close to 40% more oil, but we didn't stop there. We optimized the solution, and we managed to add another 30% on top of the previous 40%. So overall, with an optimum injection scenario, we were able to increase the total oil production by around 70%. Okay, let's review, what we did and what we were able to achieve. So through this study, we did a seamless multidisciplinary approach between the geomodeling tool and the reservoir engineering, the dynamic modeling. And the tools that we had at our disposal helped us to increase the water flood NPV by up to 60%. And also another 30% on top of the base water flood design. Remember, the water flood design was 40%, and then the optimization helped us to increase it another 30%. And the optimization workflow using CMOS helped us to run 4 times faster. So every case was automatically generated by CMOS. There was no human interaction. You just spend some time, set up the case, and the rest is on CMOS. And because CMOS is automatically generating the cases for us, we were able to manage to run 10 times more cases. Because if we were to kind of set up all the cases ourselves, manually design the cases, there was no way we could cover the range of solution space that CMOS was managed to run. And don't forget that CMOS not only covers a wide solution space, but at the same time, it is judging the results to decide what would be the best next case to achieve the goal. And this helps us to explore a greater potential solution space. And this will help us to make our decisions with more confidence and de-risk the project. So with this, I'm gonna open the Q&A. Myself, Jeremy, and Adrian are here to answer your questions. And thank you very much for attending this webinar. And all of us at CMG are very excited to provide the solutions to the conventional space. Thank you very much.
So thank you, Jeremy and Amin, for an excellent presentation. Yes, the Q&A session is now open. Feel free to put questions in the chat. There's quite a few that came in already. We'll try and get to them all today, but if not, we will make sure to follow up with you after the session. So with that, I will ask the first question. How is the CMG performance on the cloud-based platform, if there is any?
Good question. So I'll take this one. I'm actually the product manager that looks after our cloud solution as well. So over the past year, we have had a large focus in terms of optimization of the cloud solution. So we actually have changed to a different compute node. So we actually are using the absolute latest available on that side. So in terms of run speed, you're not going to really be able to find anything on the market hardware-wise that's faster. We also have the ability of running both on a single node as well as multi-node. And so if you have a very large model and you want to spread that over 1,000 cores, you have the ability to do that on cloud. On the visualization side, we also have the ability to deploy builder results, CMOST, also on cloud. So that way everything is there, nothing is on your computers on-prem. The performance of that is just like being on your own desktop. So, good question.
Awesome, thank you, Jeremy. Next question, is there any cases, situations where there's any gaps in results of CMG versus Eclipse when using the same platform like Petrel? In cases, if there is a difference between the results, what is the solution?
Yeah, another good question. So over the years, many years, we actually developed a data importer tool. And so this was actually predicated on a lot of companies and users actually moving from Petrel and Eclipse over into CMG over time. And I think to date, we've seen like some crazy, it's like 13,000 models that have been converted through the tool. And so obviously, with all of those, we've of course updated the tooling and the conversion process in order to cover off as many combinations of keywords and scenarios as we possibly can. It's made it so robust that to date, at least through the Petrel plugin, which utilizes this in the back end, as far as I'm aware, we haven't seen any differences between those. I'm sure there might be the potential edge case, but we haven't seen it yet.
Thanks again. Next question, how can you define the injector location as an uncertainty or optimization parameter?
Great question. Yeah, I'll take this one. So for the optimization process, the location of when we're looking at the reservoir study, the location of the well is defined by the IJK value of the grid block. So the process of introducing a parameter for CMOS to kind of modify is called parameterization. So what we do is we parameterize the I value, J value, and K value of the location of the well, and then we define a range for CMOS. For instance, we have like say 100 grid blocks in the I direction, so we know that an injector well in I direction can move from 1 to 100, and the same thing for J direction and K direction. So CMOS will automatically generate multiple IJK values, which ultimately defines the location of the well, and through this it will automatically switch and move the location of the injector wells, and it will find the best answer. And also on top of this, a recent addition that we had at CMG is called grid independent wells. So traditionally the wells are defined using the IJK addresses, but a very interesting tool that we have added recently is grid independent wells. And let's say you have a deviated well and you just want to know what would be the best direction of the well, and then that would be hard to define using like IJK values, and then define which grid blocks in terms of the reservoir are perforated. But with our grid independent wells, you can just give it an angle, keep changing and rotating the well or shifting the well by a certain angle, and that will help you even optimize the direction of the well. So that is how, in this case study, IJK values which is sufficient for vertical wells. Even if you don't have vertical wells, we have grid independent wells, which is a recent addition to CMG solution, and you can also use that one.
Okay, thank you. We have a couple minutes left, so we'll probably only get to one or two more questions, but again, we will follow up with you after this webinar. So the next question, what are your thoughts on using well perm as a history match parameter? I think it is one of the most uncertain pieces of data.
I don't know who wrote that, but yes, I completely agree with that sentiment. And actually, over the past year, some of the development that we put into the simulators makes it really easy to consider that uncertainty within the sensitivity and history matching stages, because now you can actually take your endpoints, which Amin had showed, and the curvature and all of everything that go into a core equation or LHE type equation, and put those directly into the actual simulator itself. And so with it there, it's very easy to parameterize. And so you can really quickly go into CMOS and say, you know, in terms of my rel perm, these were the pieces that were the most uncertain, and just incorporate that right over.
Yeah, I just wanted to add on top of that, you know, Jeremy, actually I gave directly the answer. It's very uncertain, and that is why we have added the endpoints. And now with CMOS, you can even parameterize. Remember the parameterization concept that I explained. You can parameterize just the endpoints of the rel perm, and even the curvature of the rel perm. Because say you have no idea, you don't have any data. Maybe you just have your production results, like you just know how much gas you're producing, oil and water. And actually recently I did another project that exactly the rel perm was the unknown, and by giving a range based on the engineering judgment and the limited amount of data that we had, by giving a like a good range to the endpoints, we had no idea of the actual data. We were able to kind of narrow down a range that can represent the behavior of the reservoir. So for this uncertainty, it has always been there, it's going to be there, and one of the solutions that we have is to be able to parameterize just the endpoints, and then our simulator on the fly will generate the rel perm for you. And at the same time, if you couple it with our optimizer tool will cover a wide range of solution space for you.
Okay, thanks again. We will take one more question and then we will wrap up. So the last question, what kind of operating parameters has been optimized? Could you clarify that?
So for this case study, I think I went over the parameters. So this optimization was done on the location of the two injectors. So each injector has the IJK location for the completion layer. So we have total of 3 parameters per well, so 6 parameters that defines the location of the 2 wells. Then we have the apportionment ratio, so that's the 7th parameter, and then the completion interval, like how long the completion should be. Should be complete in all layers, or like take just a few layers. That was another parameter, and the last parameter was when the injector wells come online. The answer, I didn't present the result, but we found that just a few days after the kind of forecast period is the best time to start injecting, and the sooner the better. But totally 9 parameters were introduced to CMOS to change at the same time, and CMOS will use very complex experimental design algorithms to first generate a very optimum solution space and explore the space first, and then take it from there and optimize it. In this case, 9 parameters were introduced to CMOS for optimization.
Oh, I think you're muted, Adrian.
You hear me?
Yes.
All right. So again, thank you again, Jeremy and Amin, for an excellent presentation. And thank you everyone for attending. I hope you all enjoyed it and learned something about CMG's solution. You can take that forward into your day-to-day work. So we'll wrap up here. So you'll receive a follow-up email shortly with the recording for your review, or you can share it with your colleagues. We would appreciate any feedback on future topics, so please complete the survey that will be included with that email. So thank you again for attending our webinar on conventional reservoir solutions, optimizing your primary and secondary oil recovery processes, and enjoy the rest of your day. Thank you again. Bye.
Thank you, everyone.
Thank you all.
Have a good rest of the day. Goodbye.